Now, the final topic of today, number 3, is about exchanging limits. And the question for exchanging limits is when or if you can change the order of these two limits. I mean, this is a limit in n, and the second one is a limit in x. And notice how these are exactly the opposite order on the other side. And both of these were defined. This we defined on Monday. This was the limit value of functions, and this is a limit value of a sequence of functions. Okay, so this is our question. I mean, it looks innocent, but it turns out that it's actually subtle. And what you should think of is that there are lots of similarly defined notions: limits, sups, infs, integrals, and derivatives. And a lot of them involve this subtle epsilon delta type of definition. And you cannot just change the order of them at will. One does not simply exchange the order of limits. You have to be careful when you do that. For any one of these concepts, sup, inf, integral, derivative, limit, you can find counterexamples. But you can also find theorems that allow you to do that change with appropriate assumptions. But you have to be careful about the assumptions. So bad examples in the case of sequences. So we can define a double sequence where you have Sn and Sm. This is a little bit different from the function case, but Snm is at n plus m divided by 2n plus 3m. And there are two ways of taking the limit. If I send m to infinity first and then n to infinity, and the reverse, but let's compute these and see how things can go very badly. So first, we're taking a limit in m here, and that's kind of like forgetting about the n part, because the m part dominates, and the m's cancel, and what we're left with is a limit of 1/3. So it's exactly like order of operations, because there's parentheses around that. You first evaluate the limit inside, and then you look at what you get. Now, the limit here is of 1/3. This is a constant sequence, so this limit in this order would give you 1/3. But perceptive ones of you will notice that, or the ones that are not playing LOL and just having the screen open for fun, gives the limit of a constant sequence 1/2, and that gives 1/2. So, well, it needn't be said that 1/2 is not equal to 1/3. These are not the same. And so a simple way of saying, vaguely at least, what we mean is that these convergence happens very uniformly, very non-uniformly. It's different speeds. And if you go along the row, I mean, one way if you have this, there's a visualization way of doing this, is that you have a table of values here. S11, S12, S13, S14, S15, S21, S22, blah, 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 etc. And one of these limits, well, and with this convention, m is the rows, n is the columns, and one of these limits, say the first one here, is you first take the limit along the row, you go to limit, and then you go down. And the other one is you go down here, and then you go over. And if these rows converge at very different speeds, then there's no reason that you get the same result if you go the other way first. It's a little subtle, but it's best understood initially by examples. And there are more examples in Rudin's book, Few's book, many other books. You can just Google exchanging limits if you want to find more examples. So for example, there are extreme examples like m over n. If you first take the limit in m, what you get is infinity. So then you get first in limit in n, you get 0, and then you take the limit of that, which is 0. But if you take first the limit in m, the numerator going to infinity, then you get infinity, and limit of infinity would be infinity. So, well, these are very much not the same. So not even close to each other. There's no reason for anything to like this. But I mentioned these functions spaces, and that's the statement that we will actually prove. So fn of x, 1 minus x to the n. And if you take the limit as n goes to infinity, what you get is this f of x, which is equal to 1 when x is equal to 0, but otherwise 0. And now if you take the limit going to 0, but only taking values in the open interval 0, 1, what you get is 0, because you only see the second value. But if you do them in the opposite order, well, if you take the limit fixing an n, these functions are continuous, so you get the value at 0, so that 1, and then you get a limit of 1, and these are not the same. But of course, this is our canonical example of something that converges pointwise and not uniformly, and that's the source of our problems. So we need some sort of uniformity in the speed of convergence, and there are different ways of expressing this, but in this class, this one I want to connect it also with what we have done is we can relate to uniform convergence. So if you have functions fn that converge uniformly, and this is our stronger assumption again in red, to another function on E, suppose you have an adherent point to E, and suppose that all the limits exists of fn as x approaches x naught. So this gives different values for an. Then what we can conclude two things. First of all, the limit of f as x approaches x naught exists. We have to state these things because the limits may fail to exist. And the limits that exist, we can exchange. So the limit in n can be exchanged with the limit in x. So it's a little bit of a technical statement, but one way to think about this, we have to make sure that all the, like when we say this fact here, this thing has to exist. And that's why we have to put this kind of standing assumption that the limit exists. It's also, in practice, you don't use this statement so much because you have to worry about all these limits existing. So there are other ways of actually in practice dealing with this issue, but it's a good conceptual thing to remember. And especially when you generalize it to other things like soups, infs. If you have two soups, you can't just change the order. If you have two integrals, you can't just change the order, etc. Generalizes this idea, and it's often underlying is the same principle. So let's at least sketch the proof. There's a similar idea that we have to fix certain variables in time, but there are some intermediate steps that we need to do. First of all, we don't even know what we're saying that the limit exists here. So what should it converge to? Well, we do some hopeful thinking that let's suppose that this formula was true. So this is f of x. And we want to show that this limit exists. Well, we have to determine what it is. So this should be the limit as n goes to infinity of these quantities. But these are equal to an by definition. So what we want to really show is that the limit of an exists as limit an. But first, show that an converges by showing that it's Cauchy. So we have to find an n such that if n and m are bigger than that, we're good. And how should we find that? Well, we have to have an estimate again. And the idea is to compare to the sequence. So if we compare an to fn of x for some x that we have to choose, fnx minus fmx, and then fmx minus an. So there are three terms here. These we can make small once we know n and m, because we know that the limits exist by choosing good x, by choosing an x. The question is the middle term. How do we make that small? And that term, So I'll skip the first and the last. There's a way of comparing this to the limiting value. So you add the f there. And then this last term. So the second term, we do this estimate. And so how do we choose these values? Well, we want to make sure that this is less than epsilon over 4, and this is less than epsilon over 4. So let's choose an n so that fnx, fnz minus fz will be less than epsilon over 4 for all n bigger than n. Okay, now if n and m are bigger than or equal to n, then we get this bound. And okay, we get now an minus fnx plus epsilon over 4 plus epsilon over 4 plus am minus fmx. But now, this step I'll be a little quick because we have almost out of time. By now, at this point, we're still free to choose an x. We haven't fixed it. By choosing x close to x naught, we get that this is less than epsilon. So this point you'd have to argue a little bit. How do you choose that? Well, this is converged, fn is converging and fm is converging. So using the definition, I don't want to get to that. So again, there are many choices here. There's choice of n, but it's driven by estimating these terms. And that's the skill, that's the main lesson here. Okay, then, okay, we've identified the limit, then we have to show that the convergence actually holds. So this is equal to the limit as n goes to infinity of an. So if we want to show this formula, we have to show that this limit is true. And okay, we have to fix an epsilon. We have to say that once x is close enough to x naught, then fx is close to a. And again, there's an estimate driving this. Let's see how can we estimate? Well, we can compare to the sequence again. So a can be compared to a of n. We know it's converging by the first part. an can be compared to fn of x, and fn of x can be compared to f. And now let's look at, can we make these small? Well, we can make this small because the limit as n goes to infinity of an is equal to a. So we fix an n1 such that if you're bigger than n1, a minus an is less than or equal to epsilon over 3, because we have 3 terms. Then we need to make the third term small. We do that by fixing an n2 so that if n is bigger than or equal to n2, and for every z in your space that we in E, I'll just go half a minute over time, that we have f of z minus fn of z is less than or equal to epsilon over 3. And okay, then these give us 2 conditions for the first and the third term. But again, this n is kind of a dummy variable, so let's choose n to be the maximum of those 2. And then using that, we can choose a delta so that if distance x to x naught is less than or equal to delta, and x is in E, then these two together imply that an minus fn of x is less than epsilon over 3. I mean, this is stating the limit value definition that we discussed on Monday. So with these choices, if you have distance from x to x naught is less than or equal to delta, then we get that f of x minus a is less than or equal to epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is equal to epsilon. And it concludes this lecture. So The main question here, it's easy to get lost. But the main question is, can you make these small? And you have 3 terms. Each of them, you have a different way of making them small. This is for some large n. This is for some large n. And the middle one requires x to actually be close to x naught, but depending on the choice of n. So thank you. If you have any questions, I'm happy to discuss, but the content is over. Sure, Priscilla. So here, if we take the limit first in n, then we have the limit of 1 minus x to the n, and that's either a limit of 0 when x is equal to 0, limit of 1 when x is equal to 1, that gives us 1, or it's a limit of a power with absolute value less than 1 in the base, so that gives us 0. Now, so this gives it, let's add a detail here. This is equal to the limit as x goes to 0 of x in 0, 1 of f of x. But x is only in 0, 1. I'm excluding the endpoint here from E. This is my set E. This means that because, sorry, I wrote this wrong. X not equal to 0. Or rather, x is in the open interval 0, 1. So when x is in the open interval 0, 1, or half open even, then what we have is that the function is equal to 0, so we're taking a limit of 0, and we get 0. The other direction is, okay, we limit n goes to infinity. And now this is fn, this is limit as x goes to 0 of fn of x, but fn of x is continuous. So the limit is equal to fn of 0, but what is fn of 0? It's just 1, which is equal to 1. Now limit of 1 is equal to 1. Did that clarify, Priscilla? So this is one direction and then the other. Yeah, no problem. Any other questions?